Okay. Great. I'm going to be talking about this library that I've been working on called PureScript Incremental, and a related library which uses it to implement a library which tries to replace the virtual DOM, to use incremental rendering to make a replacement library for the virtual DOM. So is the font size reasonably readable? Hopefully. I'm going to read through it anyway. So the problem I'm interested in solving is, suppose you have some computational problem and you do some work to compute some expensive function, and then you want to compute that thing again. Then if the thing you pass in as the input to that function is very close to the thing you started with the first invocation of the function, then hopefully the outputs are close too, right? Then we don't want to recompute the entire expensive function. We want to try and reuse work. So that's the idea behind this PureScript incremental library. Okay. So as a quick example, let's say you write SQL queries in a database and you have a sort of customer product order type thing, like standard example going on. And you have a products table and it has a cost, let's say, and you have a type. And I want to select the minimum and maximum cost of all rubber stamps, for example. Okay. So this is like a statistic you might compute. And this is a really simple example, right? But the idea is that it should extend to more complicated examples. Now, let's say you got a new product in the product table and you wanted to recompute this thing, but you had 1 billion products, let's say. Convoluted example. You don't want to have to recompute the entire statistic and do it, a sum over 1 billion rows. If you were smart, you would just, take the minimum of the current minimum and the new product cost and the maximum with the new product cost and update the stat in place, right? So this sounds all right in practice. It sounds all right in theory, but then in practice, it gets it's basically you basically just do a mutation in the database, right? And at scale, it becomes tricky to sort of keep track of the mutation. So we want like a principled way in which to do computations like this. So like even something like this, just like a step more complicated. Let's say you have orders and customers, and you want to see all of the, like say, the sum of the order totals from all orders from customers in California. Right? So this already is getting more complicated, right? So let's say you get a new order, then you'd have to join in the customer table. You'd have to say, okay, is this customer in California? If so, add the sum to the running sum, put it back into an update back into the stats table. Otherwise, do nothing. Right, but the point is we can come up with this like compositional way of doing incremental updates based on like the structure of the computation. Okay, so instead of like recomputing heavy computations like again and again for different inputs that are similar, the idea is that we want to be able to compute changes in outputs from changes in inputs, right? Because if the inputs are similar, hopefully the outputs are similar too. Stop me with questions, by the way, because this is pretty short. So there's this paper that I really like called The Theory of Changes for Higher Order Languages, Incrementalizing Lambda Calculi by Static Differentiation. And it basically solves this problem. And what I'm going to talk about is basically applying this paper to PureScript. So it defines this incremental lambda calculus, okay, which is a model of the lambda calculus. So you have simply typed lambda calculus. So you have types and terms, and the terms are lambda abstraction, lambda application, variables, and then you have term formers for basic things like tuples. Okay, and the idea is that we want to take the operations of the lambda calculus and interpret them in this new context. Okay, so instead of regular types, like regular PureScript types, what the paper talks about is extending types with this thing called a change structure. Okay? So a change structure is a monoid of changes, and the monoid acts on the carrier type. So the carrier type is the actual values we're interested in. So let's say relations in a database. Okay? And the monoid of changes is, let's say, a list of updates to that relation. Okay, so the list of updates act on the relation. Okay, and ideally they act in this way that's, say, it acts transitively, which means there's always a way to, you can always sort of compute a minimal diff that, like, given two states, you can sort of compute the diff that goes between them, right? But that's sort of, for my purposes, it's unimportant, but the paper talks about that a little bit. So in brief, this is what the PureScript API looks like. So we have a relation between two types. Most of the interesting stuff is on the left. The right-hand side deals with this acting transitively idea. on the stuff on the left, you have this relation between types and their chain structures. So we have a carrier type A, so like relations in a database, and DA, which is like the changes, like updates, like let's say lists of updates to that relation. And you have a functional dependency from A to DA, so that's just helps with type inference, but it means that the carrier type determines the type of changes, and it's required to be a monoid. And then we have this operation called patch, which says if I have a value in the carrier type, so if I have an A and I have a change, then I can apply the change to the value and I get back a new A. Okay. And then I said we had like standard lambda calculus stuff, right? So there's unit types and tuple types, and then there's a bit of boilerplate for those. So if we want to patch, where is it? Sorry, instance patch, tuple, right? So a tuple of patches makes a patch for a tuple, right? And if you want to patch a tuple, you give a patch for each side and you apply them independently. And then the paper gives a bunch of examples for interesting stuff like bags, which are like sets with duplicates, right? So they have these like families of data structures that like behave nicely in this incremental setting, and they give a bunch of examples. Okay, so in brief, we interpret each type as a type with a chain structure, which is this monoid of changes that we want to, be able to use to act on this type. And then the way the paper works is they construct this source-to-source transformation. So it takes like syntax trees in like some ideal lambda calculus, right? And then like turns them into this lambda calculus in this incremental setting. So this thing relies on this like code transformation thing, right? Like it takes ASTs and it produces these ASTs in this incremental setting. So a little bit like, it works nicely for the purposes of the paper, and you can prove that like it has all these properties that you want. But like, I don't really want to use this for writing libraries because I don't want to have to make my users have an extra compilation step, right? So PureScript Incremental uses a lot of these ideas, but it tries to use this embedded DSL approach. So an embedded DSL is one where you sort of use the types and the terms of the host language, PureScript in this case, to interpret, to provide the setting for your DSL. In particular, PureScript Incremental uses this idea called higher order abstract syntax, which means that the binding forms for my DSL, like the ways in which I construct functions, naturally use the binding forms from the host language. That is to say, incremental functions in my language are just PureScript functions, and I'll show how that works. And it's inspired by this idea from automatic differentiation. If you've seen dual numbers before, it's basically that. You might have seen this similar sort of idea. So instead, what I do is I take these chain structures DA that act on these types A, and I make this data type that's really simple called a jet. And a jet is, let's say I have a value, and it has type A, and I know that it's about to change, right? So I have some model type for my relation in my table, and I know like I have this conceptual model of this is where it is, and it's sort of like got this vector saying this is the change that's about to be applied to it, right? So I just pair those things up. I have a jet is a value A with change DA that's about to be applied to it. Okay. And the paper gives this sort of this representation for the function space, and it turns out that you can translate back and forward from their representation into this representation. So, which is probably easier to see on the next slide. Yeah. So my representation of an incremental function from A to B is just a function from jets to jets. Right? So that's what I'm saying. We use the binding forms from the host language, right? Like functions are just functions. Like incremental functions are functions from jets to jets. Okay. So if I have an input that's at A and it's about to move by DA, then the jet function tells me, well, A corresponds to B. That's just like running the function normally, right? But when you change it by DA, on the output side, it's going to change by DB. Okay. So that's how you can think about these jet functions. And there's this way of going back and forward that I just showed, this jet and unjet, that takes you back and forward from the representation in the paper. But it turns out you need this extra condition on jet functions, right? Not every jet function is a valid incremental function. You need to be able to say that basically patching commutes with this with your jet function basically in this way. It's not terribly important, but you have this extra condition. Okay, so just in summary, we've got these chain structures. They tell us how our types change, and then we're concerned with these jet functions, right? So jet functions act as our embedded version of incremental functions in our embedded DSL. Okay, and then we can just start inventing data structures, like incremental data structures. Right? So maybe I have some abstract data type IMAP, and this is one of the structures in the library. And I can have a change structure of map changes that act on it, right? So if I have some key, then the way I can act at each key is to, I can either add a new value of that key if it doesn't exist already, or I can remove it if it's already there, or I can apply a change structure for the value type that's inside. Right? So this way I can take the value, the change structure that's on the leaves of a map and turn it into a change structure for a map. Okay, so the change structure for a map is a map from the keys to a list of map changes for each key, right? And you can write these instances. And then you can do like relational algebra this way, right? So I have a conceptual version of like relational algebra. I can do maps which are like selects and filters, which are like where clauses, and joins, which are like joins. And just have this sort of mini relational algebra where everything's incremental, right? And I can model that situation before and say, you know, if I have products and I add, you know, I have a delta on the input side, but adding a single small product, then hopefully when I get to the output side of my jet function, it says just add the result to the sum, right? And then the thing I've been working on lately is this incremental DOM idea. So the idea is that we don't want to have to recreate the DOM on every single new model that we get. We should be able to say, here's a little change to the model, and run it through a jet function that produces a change in a view, and then patch the conceptual change of the DOM onto the actual DOM. Right? So you just come up with like this view type, which is basically like a virtual DOM type thing. You know, like the type of DOM representations you might find in a virtual DOM library, and a change structure for it, right? So this is almost just derived from the type, actually. Like you just go over the record fields and take the change structures. Remember, like a change for a tuple was a tuple of changes. So a change for a record is, you know, a change for every thing, every label in the record, right? And the idea is that your application just becomes a function from a jet function from some model type to some view type, right? So I can either run it normally, I can take a model and get a view and just build it onto the DOM like a regular virtual DOM library, or I can run it in incremental mode. I can give you a change to the model and get a change to the DOM, and then take that sort of conceptual change to the DOM and apply it and actually get a real change to the DOM that I can apply. So yeah, that's what I've been working on. It's in PureScript Incremental. The DOM stuff is in a library called PureScript Purview. And then there's a whole bunch of other stuff I'm sort of interested to apply this to. So database I already mentioned. Incremental parsing would probably be a good one. So if you think about something like syntax highlighting in a text editor, you know, you make small changes, and like conceptually, you know, like I didn't really change any of the lexemes when I like, you know, insert a character in the middle of a lexeme or something, right? So like hopefully we can make the machine realize that those things don't need to re-lex the entire file or something. It can be like a, you know, we can use these jet functions to incrementally lex files or something. And then the other one I had in mind was canvas graphics. So like if you think about something like, you know, if you have like a system of objects on a canvas or something, and I drag one around, I don't need to render everything that's away from the objects I'm dragging. I really just need to invalidate a little rectangle, right? So there's like, you know, normal systems for like canvas graphics have like invalidate rects or whatever, and like, but it's sort of unstructured, and I'd like to think this would give a bit more structure to something like that. I think that's all I've got. So, yeah, questions? Yeah.
So you began talking about how you don't want to recompute the same values over and over again. You want to compute something just once, and so you want to find an efficient way to move from one state to the next. So does this incremental DOM, are the applications purely in performance, or are there ways, like, does this allow the programmer to structure the program in a better way, or like write less boilerplate or something like that?
Okay.
Any other benefits?
Right. So actually, for the DOM case in particular, like the benefit I wanted was not performance in the sense of like, you know, avoiding expensive work. The expense with the DOM is like actually patching the stuff onto the DOM, right? You want small diff sets that go like to actually apply to the DOM. You don't want to be like thrashing the DOM with like hundreds of unnecessary updates. So in a sense, yeah, it's about performance, but like doing the computation to get to that point where I have this like small diff set, that might take some work, right? Like maybe I even move that to the server. Like that's another interesting thing with this approach, right? That the change structures are just data. So like I can like serialize them and move them around and stuff. Yeah, so it's not necessarily about performance in that sense, but like ideally you have some like something that is expensive and like yeah, it's the application of the patch at the end that could be the thing that you like that saves you work, right? That's what I wanted with the DOM thing. With the relational algebra thing, you want to come up with small amounts of work to do on update rather than doing entire table scans or table aggregates or something. So yeah, it might not be a performance win, obviously, but like there might be some some way in which it's a performance win. Yeah. Any other questions? Yeah.
Are there any places where it's not usable on the DOM, like any particular operations that are not supported?
Right. So it's very basic at the moment, and I'm sort of still doing a lot of experimenting with it. It seems like most sort of simple applications, like I can do sort of a to-do list, and that's I wouldn't use it for anything too crazy. Like I'd probably start with something like I'm going to basically try out a bunch of things and like see where I run into issues. The nice thing is, I think it'd be a nice fit for like components that are written in JavaScript that you want to interface with, right? Because like these chain structures are like good models for like mutation generally. Like I don't want to say that. Like you have some like resource that you want to interface with. So let's say you have like a charting library or something, but it's got some like opaque JavaScript API. So you just make like a chain structure that corresponds to like, okay, these are the patching operations I can do onto this existing chart or something, right? And then I can like wire that up to like some like nicer simplified model of a chart or something and push it through a jet function, get the changes and apply it. So I think it could be applied to some like complex stuff, but it wouldn't necessarily be exactly the way I've done it in the library. You might need to invent some new chain structures to model some of the like more real world stuff that you might want to use.
Are those chain structures in the shape of a tuple?
No. So actually, yeah, that's kind of interesting. So you can do things like sums, right? So like all the ones I have are actually tuples, right? Like the map thing is like you have one thing for each key, and like you change each key independently. Like you can imagine having like incremental booleans or something. When it gets interesting is, let's say I have like an incremental if then else function, right? Then I have like, if the boolean is true, then I give you one value of type A, else another value of type A. But the boolean is incremental, right? So I can change it from true to false. If you allow that change, then I have to be able to turn any arbitrary A into a new arbitrary, because I go from the true state to the false state, right? So that's when I start requiring, where'd it go? That's when I start requiring this diff class, right? Because then I need to be able to like arbitrarily jump between states, and that's when having this transitivity property becomes handy. So generally, I've avoided having sums for that reason, and I stick to tuples because it's like enough for the DOM case. But yeah, you can do it. Just there's a little bit more machinery needed.
So you have a law that your jet functions have to satisfy, like a jet A to jet B.
Mm-hmm.
There's a law that dissatisfy. So things like monads and functors, they also usually have laws that they have to satisfy. It's kind of like if you're implementing a monad, it's kind of hard to screw it up in a way that the laws don't work. So, but I imagine with these jet functions, like how difficult is it to actually make sure that you hit the coherence condition, and how much checking do you have to do?
So I haven't done any quick check testing with this for the laws, which I definitely should, but so that would be interesting to do. I've basically just been doing sort of, I don't know, like I've basically just been doing sort of like unit testing essentially, and like I feel like if the structures you come up with, like the maps and the arrays and stuff, like behave sensibly for on like a decent set of operations unit testing, like it's probably, I have a feeling that that's sort of capturing the law, but the intent of the law, but like I should test that. I should be quick check testing.
So you start with like a vocabulary of like safe data structures and safe operations on them, and build up from there, and just you can't say it works from there.
I hope so. Yeah,
okay.
I haven't tested it yet, so we'll see. Any other questions? All good. All right.
Okay, we're gonna get started. Cool, so this is gonna be much more basic in comparison, oh, that was bad timing. Did I wait again?
Project.
What? I just did, but yeah. Okay, well, we'll give it a try. Just raise your hand if you can't hear me. So we've been working on this PureScript React basic library, and I'll mention regular PureScript React again later, but the basic idea is that we wanted a playground for us to try some different APIs, simplify a little bit, because we have 2 existing React apps, and we wanted to build a component library and share that between the 2 apps and make it just a little bit less friction to convert an individual component. So that's kind of the main motivation. But yeah, just kind of experimental, I guess. So here's a basic component example. Actually, that is out of date. So let me show you this one. So anything with the type React component is going to actually be a React component that you can use in JavaScript the same way you'd use it here, same way you'd use it in React or the regular PureScript React app. So if you were going to use both together, you could just unsafe coerce them basically. The only argument is the shape of the props, and the main difference here with regular PureScript React is that this is a record type, not an array. Then you can put anything in there that you would normally send to a DOM component. For example, if you're working with the basic DOM string components, not like one that you've built custom. So this one is a custom component. You use this React function, and then you give it this record here with a display name, which is just for debugging, an initial state, which also needs to be a record, and this receive props function, which is kind of our simplification of React lifecycle. So if it doesn't fit into this pattern, we still have to switch to FFI, but for us, this has mostly been enough. So the way this function here works is that you get props as the first argument, you get state as the second argument, and you get set state as the third argument. And it's actually exactly the same for the render function, but the receive props function can have side effects. So any setup, teardown, responding to user stuff goes in there. And then anything imported from React Basic DOM, we have all the regular string, like HTML components that you'd use in React. And they all take records. The one thing that's kind of neat about these is that they're set up in a way that makes all of the properties optional. But if you provide the property, it has to match the type. Yeah. Maybe. I can choose a different resolution. Yeah, hold on. Better? Okay. So here we're just rendering a button. It's got an on-click. Because underneath, this is just JavaScript React, we have to give it this regular React function, unwrapping the F in PureScript. So all of these handlers start with make F function 1 if you're just doing the basic stuff. And then we update the state here. So yeah, that's the simplest example. We've got it running over here. The button, you can click on it. Also, these are in the examples folder of the project. So there's one that demonstrates using a nested component, which is nearly as simple. So this is the container. All it's using is this create element function to take anything that has that type React component and then the props that you want to render it with. The built-in DOM things like that div there, it's exactly the same thing, but create element is pre-applied. Pre-applied to a string here. And then, oh yeah, so we have that one lifecycle function where you have the initial state and you have the receive props function. But if you're writing components that don't deal with state, this is just a shortcut for basically setting those to no ops. So that's all. And if you use it, the render function only gets props. It doesn't get the other two things passed in. And then this would be the component that it was actually rendering there. So the props that are being passed in is this Boolean for whether or not the button's on or off. So here on receive props, we receive, this would be if the parent re-rendered the child component. We have to take that and merge it into the state if we're keeping track of it in that component state. This is kind of an oversimplified example. Yeah?
So the life cycle has all that set up. How does it tackle care?
There is no unmount life cycle. So if you're doing kind of like weird FFI stuff where you need to like modify some HTML or unhook events, like if you're doing on clicks here, React handles those life cycles. But if you're doing your own manual life cycles, you'll need to just go back to JavaScript.
You put that at
You would just write that component in JavaScript and then write this line right here for an import that component. Yeah. So we try to keep the API as simple as possible and then just say all of those edge cases, if you need refs, if you need context, you'll have to do that manually. Because it's pretty easy to create these little wrapper components that abstract that stuff away if you need to. Yeah, the one other thing I want to show here is this controlled input example, which is one of the first things you'll encounter going through just React's docs. And one thing that's a little bit complicated, like an edge case of the React event API, is that you're only allowed to touch the event object synchronously in the event callback. If you try to read from it after that, it'll blow up. And I don't know all the reasons for that. They basically have a wrapper that's a proxy that has some performance implications, but also normalizes the shape of events across browsers. Huh? Oh, okay. Okay. Cool. So this is going to be hard to see on this little screen. But this line here is the one I want to talk about. So remember on the other example, we had makeF function 1, which is kind of the raw way of like directly creating a handler. But the event type that we pass into that handler, I can show you over here on the docs. So this event type is a synthetic event, which is React's event, but it's an opaque type. You can't do anything with it. And so the complication is that if we have functions in here that are like you can read the event value, but the return type is F because that's a side effect. The problem is that if you try and use that in this set state callback, so the set state callback is the old state as the argument, and you return the new state. But if you try and read the event value in here, React will throw an exception because you're not synchronously in the event callback anymore. This is the one other interesting type thing going on in this library. This event function type here is a wrapper that basically takes away direct access to those event properties and presents them in a way that's safe to interact with. So you have to tell it up front everything you're going to do with that event object, and then you get the values that you want back out of it safely. So the way that works is here we create a handler, and the handler takes that event function. So you can compose any operations you want to do with the event as the first argument, and then you give the callback as the second argument, and you'll get passed into that callback whatever you decided to pull off of the event. So in this case, we're going to prevent default, which would normally be a side effect, and then compose that with this merge function, because no library would be complete without Rocon's stuff going on. And basically what this is doing is each of these are values that you can pull off of the event, and they're being used here to also create a record. So this record is going to have property names matching these names. So in this callback down here, we get the timestamp and the target value passed in off of that event. Does that make sense? Have I like completely lost everybody? I feel like it's really hard to see on the screen. A little better? It's always up front. Yeah, that's another edge case that you'd have to do in manual FFI, which you could still do, like if you wrote an FFI function that was synthetic event F unit, you could just pass it in here. Yeah, there might be a way to write one of these event function things that takes like a conditional value. Yeah. Oh yeah, the one last thing I was going to mention was the regular PureScript React library and how this was kind of like an API experiment. And the thing that I thought was kind of interesting is that we kind of settled on this function here as being sufficient for most use cases. And a future version of React is going to add a very similar function and replace two of the existing lifecycle functions. And there's also a change to how refs and context both work. So yeah, maybe we can reunite the good parts in a library that's compatible with React 17 or something. Yeah. Uh-huh. Yeah. Oh yeah, this one. So basically this component, it uses state, but it's only actually modifying state in the render. It's not modifying it in the render function, but it's only modifying it in the event handlers that are nested under the render function. Yeah, so we actually effectively don't use this, but because we have state, we have to pass it in. So this is just, it doesn't do anything. It ignores, yeah. And this function wouldn't make a lot of sense if there were props being passed into this component up here, because you'd want to merge those into your state somehow.
No, why the arguments? Because they're just like, I mean,
just this useless function here. Yeah. Yeah. In practice, this ends up not being super common. Because usually if you have state, then you have multiple ways of updating it. And usually there are more props than nothing, so. Any other questions? Cool. Whoever's next.
We're on the stream. And I have to set up my view. Okay, and I'm Thomas, Thomas Honeyman. I work at CitizenNet with a few of these guys. We're a machine learning ad tech company based here in Los Angeles. We build a lot of our front end in PureScript using Halogen. And because of that, you guys have probably seen, if you're in the PureScript Slack channel, you've probably seen me bugging Nate or Phil or somebody about type issues as we migrate from Angular to Halogen. I'm kind of constantly asking questions there. And this talk is kind of a culmination of a lot of things we've learned as we've been migrating to Halogen. And so because of that, working with Halogen, it's a component-based architecture, a bit like React. And so we spend a lot of time working with, writing, and thinking about components. And we spend a lot of our time working with these open source UI components. And how many of you guys have brought in a pre-built component that you needed, like an autocomplete or something like that? Yeah? How many of you have tried to customize it to work the way that you want? That's you? How did that go? Pretty well? Iffy, some cases? They can be, if they're close enough to what you want, they can really work, but sometimes you can run into some real issues. And that is what some of our experience has been and what I want to talk about today. So we spend a lot of time building components, and we bring in UI components. And to illustrate kind of a common scenario that I experienced, and that many of you have probably experienced as well, is walking into work with the design team and the product management team. And they come in and they sit down with you, and they have this awesome component that they want you to build. And for the sake of argument, let's say it's an autocomplete. This is what we had to build. So this story cuts a little close to the heart here. And they come in and it's really awesome. It's got a bunch of features. There's like this refresh button that'll fetch all the data again, and it's actually in the list of items, and it's shooting sparks out the left side of the component when you load things up. Like it's some crazy thing that your designer has dreamed up, and your job is to build this thing. And so you go in to build it, and one of the first things that I reach for as a developer is I don't want to reinvent the wheel every time that I try and build something. If somebody else has already worked through all the edge cases, they've made the mistakes for me, and maybe 10,000 other developers have already filed their bug reports for it, I want to benefit from that rather than try and re-implement from scratch. And so let's say your designer's come in and he wants you to build this component. And so you reach for an open source one because might as well benefit from other people's work. And as one example of a component like this is a React Select, which is not a Halogen component, it's a React component. But with PureScript, we can interface with some of these, maybe with React Basic if we want to. And you might bring this in and say, you know what, this is pretty close to my designer's model. He wants this icon over on the left side, and he needs those sparks flying out the side, of course. And there needs to be that refresh data button, but otherwise it's pretty close. So I want to leverage his work. And then you get into customizing it because while it's close, it's not all the way there. It works right, but it doesn't look quite right. And so you go in and you're starting to try and work on the icons. Oh, this is very difficult to see, but it's not that much better when you can actually see all of it. Honestly, you basically have this tree of HTML that the component is rendering on your behalf, and you can hook into these CSS classes and style it as you see fit. And with some other parts of it, you can go in and you can work with this configuration record that might say, you know, does the menu open to the left or to the right or whatever else. And so you have a chance to configure it, but what you're really importing is a bundle of code. And oh, thank you very much. We now have some more, oh, you still can't see it on the stream, but it's a good effort. You have this bundle of code that you're bringing in, and it's offering you some functionality, and it's also offering you some HTML structure. And so you might be able to shoehorn with these CSS classes, you might be able to grab this select arrow zone, which is down here at the bottom. You might be able to say, you know what, I'm going to style that to actually be like a search icon, and I'm going to put it on the left with some fancy positioning. And the sparks, we're going to have to give up on those. But the refresh button, you know, there's no way that the library author has not accounted for literally every possible thing that somebody might want to do. So there's no way to do it. So I have to go back to designer and either say, I'm going to put the button outside the component, or I'm going to have to write this component from scratch myself. I'm going to actually have to write an autocomplete. And this is a problem that's particular to UI components, and it's not one that's true of bringing in any old library. So if I reach out and I need to do some validation or something like that, and I want to pull in an external library, usually I can have it kind of unintrusively augment the application code that I'm writing. I can write a bit of code, and I can run the validation on it, but I don't have to like re-architect what I'm doing. But with UI components, a little bit different. Because of all this HTML and all this structure that I'm kind of coming into their playground, and I have to try and work with their code that they've written. I don't have an easy way to just take their code and augment what I'm writing. So kind of the onus is on them first. And if they haven't accounted for my very specific use case, Sparks, for example, then it's no good. I either shoehorn it or I have to fork the library. Oh, sometimes I turn off my computer in frustration. And sometimes you just end up having to write your own component from the end. And my argument is that a big part of this problem and why it happens is precisely because it gets around, it renders that HTML for you, which can make it extremely difficult for you using a third-party component to control exactly when, where, and how it's going to render. If it's close enough, if it's really close and you're just changing one of the icons and putting some border radius on it, you're okay. But if you want to get any bit further than that, you start to run into some inflexibility. Which kind of answers the question of what if the component didn't render anything for you in the first place? What if it stopped before it got to that step? You went in and you wrote all your HTML and your CSS. You made it look exactly like the mocks. You made everything spec'd out perfectly. It's completely static. It's a useless component. It doesn't do anything. But then you can augment it with a few behaviors and turn it into a functioning component. But you never had to compromise on the design that you worked on. This is the key idea behind a library that a few of us here are working on at CitizenNet called PureScript Halogen Select. And it's a library for building, it's basically a single component for building selection user interfaces in Halogen. And it allows you to do things, what we use it in production to build this type of head, for example, with plenty of custom rendering, as well as drop-downs, calendars, image pickers, pretty much anything that involves a group of items that you can select. This library can help you do it. But if you look at the code for the library, which I encourage you to do, that's the link to the documentation site out there. If you look at the code, you won't find a render function anywhere in there. It's actually a Halogen component that doesn't have a render function. And so this leaves the user of the library to come in and write that for themselves however they see fit. Now, there are some benefits to this, and there are also some drawbacks to this, and that's what I want to talk about today. But before I get in too far, I wanted to make it concrete. I thought we could take this idea and build a type ahead together and see how that works out. As I go through this, there's going to be some code snippets. Please ask questions if you need to. You can stop me at any point in this process. Also, every time you see like a big slide that's just a sentence, it's a good time to ask me some questions as well as a stopping point. In the meantime, I encourage you to check out the docs site and play around with them if you have your laptop with you and see how all the key events and everything pick up for you. And then when we go through the code snippets, you'll see how you get most of that functionality for free without having to compromise anything about the way you design it. Any questions or clarifications so far? With me? Okay. Now these code snippets have a different theme, and I'm hoping that they show up a little bit better. Yeah. Okay, can you guys read this? Yeah, okay, that's a little bit better. So yeah, we're going to write a type ahead. And so what you're going to see here is a bunch of code from Halogen. And as we build this, this is actually a real type ahead that we have. So by the end of this time, when you see this, by the end of it, you actually have a real working type ahead that you could use in your application. And to start out, the first step would be to just actually write the HTML, almost as if you had no library you're bringing in at all. You might render your type ahead to have an input field, and then underneath it, a menu, and inside of that, some strings, things that you can select. Maybe like our type ahead, it's a list of Star Wars characters. And as you do this, all of this is just static HTML. you almost don't need the select library at all, except that you'll notice that the type signature here is the select component's actual render function. So you're writing the render function for the component, and then you're going to pass it in. So from this, you can use anything that's available from that component state. And the most important things here that we're grabbing are, let's see. First, we're grabbing the highlighted index. So if down there, when we render an item, if this item is the one that is highlighted, we're going to add a CSS class. Say this is a highlighted item. And the menu, we're only going to show the menu if the visibility for the component is on in the first place. And so you end up being responsible for writing this. However, this is like the most minimal basic example you could. If you needed those sparks and you needed that button, you can embed them just as easily in here because you're just writing HTML at this point, and you're writing CSS. You're not trying to get Bootstrap to work with some structure that already existed. You just get to write it from scratch in the first place. But at this point, we don't have a component. Like what we have is some HTML with a fancy type signature. To actually make a component, we do this. And if I move it too fast, you might miss what's going on because there's really little. It's almost identical code. And that's the main selling point of this library, is that you're able to go from just your static HTML that you've designed however you like and turn it into a functioning component with very minimal footprint from the library. And the main things is there's 4 of them. I talked with some of my team earlier today and said 3, and they called me out because we actually added an import at the top as well. And the import kind of shows off what's going on. So we've imported 3 functions, and all of them have this name of set props. So set input props, or set container props, or set item props. And if you see where they're used, with set input props being used on the rendering for the input, set container props being used on the menu, on the parent node of all those items, and then finally set item props being used on the item itself. Is anybody able to take a guess as to what these functions are doing? How they're augmenting the behavior here? I'll give you a hint, and the hint is actually going to be the full answer. These props are just this. They're a collection of event listeners that are triggering queries inside the component. So this is something that you would write in Halogen all the time. You write on click, I want this thing to happen. I want this query to trigger. And all that we've done is pre-written with some helper functions a set of queries that we want to trigger from events. So when you tab onto this input field, we want to capture a reference to it, and then we want to set the visibility of the menu to be on. Now your render function that you wrote, because you wrote this HTML here, your render function already cases on this. You already are handling, you've decided what you want to do based on this state. And you've decided, in this case, not to show anything at all if the visibility is off. So what this will do is, with your render function's help, this will actually turn on the menu. And at this point, you actually have, with these helper functions, a component that really works. And you still need to actually store it somewhere. So now we're going to get back on some familiar territory in Halogen. And we're going to move to the parent component that actually owns this child. And this parent component is going to mount the child component here. So the select.component. We're just going to mount the component. And all it really does is renders some selected items. Actually, I'll go back, and we're going to use this as an example. We're basically writing this type of head. So the items that have been selected stack up on top of the type head. And the items that are still available to be searched are in the menu. And so you've written here your type head component. And in the parent, you set a div that's got a full width. You run the selections on top of the component. And then you mount this autocomplete that you've built with just your static HTML that you augmented with our few helper functions. To do that, the input for the component to your configuration record is pretty minimal. There's no display options at all. There's nothing really to worry about because you've provided the entire render function in the first place. There's no CSS classes that you have to think about or hook into or anything like that. You send in how long you want it to debounce, what your items are, and then your render function, and you're pretty much good to go. This brings us to the last step, and this is still unfamiliar territory for Halogen components, which is managing the messages that are output by a component. And this is important for any component to actually do something based on when something important inside the component has happened. And in select, as we're dealing with user interfaces where you select things, we only have 3 that matter. So the 3 cases that you have to handle are first, when something is searched, which is the second case here. And here we've written like the full implementation for the type head. I don't know if that helps at all. When a new search has been performed, we're just going to filter out any item that doesn't match the search and then set new items inside the component. When a new item has been selected, we're going to add it to our selected list, and then we're again going to filter out the items that don't match. The third case is a little bit weird, and this is a message called emit. And emit allows you to embed your own queries from the parent into the component. So rather than being this opaque component that you can't extend the functionality of, if you have some action like you want to hit the database, refresh all the data, then blow sparks out the side, you're totally free to do it because you can write that functionality in the parent and then embed the query. When something is clicked, it'll raise that query back up to you and you can evaluate it recursively here with eval query. To make that a little bit more clear, I want to go back to the original HTML here, where we had in the render item, we have, oh, there we go. This will work as a pointer. We have this on click, we want to do an action, and we want to refresh all the data in the type head. And this is something that the type head doesn't support. The select library has no concept of refreshing data at all. But you need it for your functionality. And so you're able to do this by writing in your parent component's query, this refresh all data, some handler for it, like hit the database and then sends it in new items. And then you need it to be able to run inside the select component. So you wrap it in this constructor called raise. And what this will do is when the item is clicked, it will trigger this emit message. And the emit message contains a query. And the query that it contains is refresh all data. So when you call this eval query here, you're calling your own query that you've defined, which basically means that anything that you can run in the parent component, you can run inside select as well. And that's it. We've just written an autocomplete. And you get all of the behaviors that are involved, like highlighting and keyboard events, screen reader accessibility, whatever, all those sorts of things come in. And the intrusiveness into your application is that you might have had to write some extra handling around this. You have to handle these messages, and then you have to use 3 set props functions to attach into your HTML. So the type head that we just worked on together in a very short amount of time is here. It's in the repository. It's one of the example components. We basically wrote the exact code. There's give or take 20 lines. That's mostly rendering stuff. And that's pretty much all that goes into writing one of these components. And the main crux of the argument that I have today for you guys is that we should design more components to not have render functions, to defer that as an action that the user gets to decide entirely, and then just augment that with their own behaviors. And I just ran you guys through kind of a lot of lines of code with very little explanation. Are there any bits of that that kind of got glossed over you want me to go back to? Or?
I'm just interested, why did your place start using PureScript? Why did you just wake up one?
That's, okay, that's kind of a long story. And it may be a story that's too long for this part of the talk. I'll give you a short answer, and then at the end of the talk might be a good time to come chat with me, Dave, Forrest, and Chris. We all work at CitizenNet. These guys are migrating, or were migrating from Angular to Halogen. And then I'd been working in PureScript for a while, and so I joined on board to help facilitate that process as well. Luckily, I don't have to touch the Angular too much, so I mostly do PureScript stuff. Yeah. Any other questions about what I've talked about so far? Yeah, we haven't specifically tried replacing any React components. React Select is just a particularly good component. It's got like 11,000 stars, and it's really nicely done. But it suffers from the kinds of problems that drove us to make this library in the first place. So no knocks on that library. It's a great component. We haven't spent any time remaking React components, but we've used this same library, the Select library, to make dropdowns, We've made the type of heads that we have, but we also made a calendar component that included like paging through different months and all sorts of functionality that is not at all written into the library, but it kind of to prove that this approach works for other select components as well. Yeah.
To kind of extend the question a little bit,
Yeah.
the pattern, that render pattern is being referred to as render props. If you search for render props or library mentions using render props, that's what they're talking about.
Okay, very cool. Yeah, so the mention being a pattern called render props. And I haven't spent very much time, I actually never spent time writing JavaScript before getting into PureScript, so I have some unfamiliar with like the React.
It was just like the last 2 months or so, like, suddenly everyone's talking about it, even though you could always do it.
Oh yeah? Oh, very cool. Yeah, at the end of the talk, I'll have a brief note about some of the inspirations for this library, and one of them is probably one that popularized this approach. But I'm glad to hear that because, by all means, as long as this approach gets a little bit more traction, I'm happy to hear it. Any others? Cool. From here, I want to walk into a few of the key benefits to this approach and why I hope that it becomes a little bit more popular in PureScript and in other communities as well. And the first one is that designing components this way gets us a little bit more to what it's like to bring in a normal open source library. And the main part of that is that you're not intimately tied up with the structure of your application or the structure of your HTML and your CSS. And what this does is it naturally brings down the size of your footprint of your API. So when the user is writing the render function, you don't have any display options to configure in the first place. And you don't have any CSS classes to hook into at all. And you don't have any structure to mess around with. So as a library author, things are made a lot simpler for you because you don't have to think about all of the innumerable design cases that somebody might want to come up with. And as a library user, you're not forced into any structure that the library imposes on you. Later on in the talk, I'll have some caveats on places where this is not as clean and simple as I'm making it sound right now. But for the most part, it does a really good job of minimizing the size of your API. We went from that static HTML that you could have written completely apart from the library to all of the props that we needed with 3 functions applied to a couple of props arrays. The second thing is kind of a follow-on from the same concept, and it's design freedom. And this is more in context of a user, in that when you write your own render function, you're writing HTML and CSS. You can basically write whatever you want. If you want your autocomplete to have a bunch of balloons spread across the page and you throw darts at them interactively and popping a balloon selects something, you're free to do it. The library has no restrictions on this. As long as you have some collection of items that can be selected, you're good to go. Finally, we get to the functionality. And another key point of this approach, and the most important one as far as I'm concerned, is that it allows for a little bit more extensible functionality. Because the render function, especially for a Halogen component, maybe perhaps components in general, is a major entry point for behaviors for that component in general, because this is where you're actually triggering those queries. You can define all the queries you like, but at some point they have to be triggered. And when you write a render function in the parent select component, you have access to parent state and queries, child state and queries. So if you need any new functionality, you write it in the parent, you write the handler in the parent, and then you just pass it into the select component if you need to. This allows you to, if, for example, you need to make a calendar, and the library has no concept of what a calendar is, you can still embed those buttons of the current date and refresh all the data and all that stuff. Whatever you can dream up in your parent component, you can put it into the child component, minus perhaps some effect rows mismatches. However, this is the point where we have to talk about some of the weaknesses and the drawbacks of the approach. But before I do, I want to go back to the previous and see, would anybody like any more clarity on these points, or is this pretty good? Cool. So, as with all design approaches, this one does have some weaknesses. One of the first is both a strength and a weakness. So you have the advantage of being able to write your own rendering code, and the disadvantage that you have to write your own rendering code. if your designer came to you and he basically gave you a mock of React Select, use React Select. It's already made for you. You don't have to do anything. Maybe you change the border radius and you're good to go. You don't have to write your whole render function from scratch. But as soon as you find yourself moderately getting away from that, especially in terms of functionality, not just the design, it turns into more trouble than it's worth to even like keep trying to get the component to work for you. You end up needing to, I don't know, write your own at that point. So if you are close enough to an existing open source component, you might as well use it. Bring it into your project. Don't worry about writing all your stuff from scratch. But if you're not, then this is an advantage of this approach. The second one is that the dream of this approach is to not impose much structure on how you want the design of your code to look. Unfortunately, you do end up having to impose some structure as a library author. For example, in Select, you at least have to have some item that can be selected. You have to have some parent container that has those items in it, and you have to have something that can capture key events. As long as you have those, you're okay, but we're still expecting some structure for you, and that can still be limited. The place where this gets you into trouble is if you end up needing too many points where you need to start augmenting behaviors. You have like 10 set props functions, and they're writing all their own code. Like at this point, you're getting the worst of both worlds. So there are definitely situations in which this approach is not going to be a good fit for a component. Finally, you as a library author don't have the render code. You don't have references to all the elements that you're working with. So for example, in Select, we need to focus and blur the input field or a button toggle. But since we didn't write that render function, we don't actually have that HTML. We can't just say, get the one with this ID or get the ones with this reference or something like that. We could force users of the library to pass in an ID or pass in a reference or something like that. What we do instead is we wait for you to focus the field, and then we capture a reference and we hold on to it, and we use it from then on. But then we have to account for the possibility that we don't have that input field in the first place, and we could run into some edge cases. So this introduces some trouble for you as a library author. In our case, it was minimal, but I can imagine other components where maybe you had some clever solution, some clever optimization you wanted to do with the HTML, but since you don't know what the structure is, you're not able to do that. So the key idea behind this talk is to focus on writing behaviors and not on the rendering code. So stop a little bit before you get to that point and treat these UI components a little bit more like a regular open source library, where you bring in functions and you can use them to augment what you're already working on, rather as this opaque bundle that you can configure from the outside, but is ultimately somebody else's code that you're trying to mess with. I have a couple of sources that were dramatic helps in writing this library. Nate, a big one, helped us out with writing this. Nicholas Schill, who's at Modern Musician in the Slack channel, another immense help in figuring out some of the type issues. The rest of the CitizenNet team who built this library with me is here. We are not hiring at the moment, but we are going to be hiring pretty soon. So if you're interested in writing PureScript and Halogen applications, talking to any of us would be a good bet. And finally, and this is where I think I first heard about render props, was the library Downshift by PayPal. They take a similar approach in deferring rendering to the user. Cool. And that's it for me. This is the link to the GitHub library. I encourage you to please check it out. It's still under active development. We have some work to do around things like accessibility for screen readers and that sort of thing, where we could use some help. If you're curious and you just want to check out the source, it's very small, like 100 lines of code for the core library. So you could learn some interesting things there. And our company is called CitizenNet, if you'd like to check out for PureScript opportunities. Cool. Before I shut down the computer and everything, were there any lingering questions about anything I talked about? Sure. I can't speak. Do one of you guys have anything you'd like to say about that?
some issue there.
Yeah. So being a component architecture was motivation versus having like all the state managed. And then also maturity. Halogen is kind of a good bet. We're CitizenNet is an ad tech company within Condé Nast, and so we are in a corporate environment. We are kept to pretty strict development deadlines. It's fun to experiment with things, but ultimately we do need to be delivering results, and Halogen's maturity helps with that as well as a convincing argument. Anything else? Cool. Well, thank you for allowing me to come in and give a talk today. Hope you enjoyed it and learned some. Please check out the repository, and if you have any ideas to make it better, or if you find any bugs and you want to file an issue, looking forward to it. Thank you.
Extensible checked exceptions with polymorphic variants. So as an overview, I wanted to look at the exception problem, which is really kind of a subset of the expression problem, which is something that's kind of that's published and talked about and is sort of like this point of flexibility in languages. And so I wanted to look at, just imagine, this is just type signature. We've got this function get, and it operates under a monad HTTP constraint. So I'm assuming that this makes like a get request. Takes a string, which is the URL, and within an accept T wrapper, which is a monad transformer, it will either return the body. I assume it's just a string, so it returns a string, but it has the potential to raise an HTTP error within accept T. And then maybe So imagine then there's another one, write, which is in monad FS, so for file system operations. This is a hypothetical function that writes similar signature, but it writes content to a file on disk. And that's an accept T as well, but it raises an FS error, which is a different type. So what happens when we go maybe to write this function get PureScript, uses both monad HTTP and monad FS, and we want to combine them together. We want to bind them together so that I can get this URL and then write it to disk. Well, I've left this type as an underscore because if you try to combine these two functions together, then you immediately get an error because the FS error and the HTTP error don't unify. So if we want to combine these two functions together to use them, then we have to map over the errors so they can unify. And so we would use something like with accept T, which is just let you map over the error type. So we have to unify them into some shared type. So in this case, I've chosen just either. So either HTTP error or FS error. But that means every time we embed these other operations, we have to use this with accept T to then map it into some type that unifies. So what if you have other layers, other sorts of errors and exceptions? Then okay, then your options are maybe you keep extending this with either 3, either 4, either 5, etc. But this, of course, gets extremely tedious. And the big problem with using something like either 3, either 4, etc., is that every time you introduce a new function that has a new exception type, then you have to go back to all the cases, all the places you used it before, and change the way you mapped it to then map it to the new type that they're all sharing. So if you introduce something new, it then breaks all of your old code. You've got to go back to your old code and rewrite it or modify it so that it then works with your new type. And that's kind of the crux of the expression problem, is you want to be able to extend it with new functionality, with new verbs, without breaking old code. Because you've already written it, it works fine. So one possible solution is something called polymorphic variants, which is a very, very jargony word. But so I want to look at what record is. So a record is a structural product type. So a product type means that you have different values of different types, but they're all in the same structure at once. So like a tuple has 2 values, A and B. And a record is just a structural product type. You can have you define what the labels are in your structure. So this is an example, just like something you use in any sort of model in your web app, like a user record. And I'm using the actual, I'm not using the record syntax, I'm using the actual record type name here. And this has polymorphism around it. We use row types. And we can zero in on like only the structure that we care about. We can add this extra type variable R, and that lets us be polymorphic in the structure of the record that we pass in, which means that we can pass in different shapes. They just have to adhere to the structure that we specify in our function, the piece that we care about. And so variant is kind of the dual of that, and it's for structural sum types. So like either has left and right, left or right. You either have a left value or a right value. So what if we apply the same row typing to sum types instead? So in the case of a sum type, this looks very similar to the record. We just replace it with this variant type. It looks similar, but it takes on a different meaning. So whereas in a record type, the labels, like the foo bar badge here, the labels would refer to the fields of the record. In a variant type, the labels refer to the tags of the sum. So like left or right. And the polymorphism we get here is that we only have to specify the tags that we care about in our sum type. So that means, so before we could pass in, like with records, you could pass in different shapes of records to a function that only cares about the fields that it tells you about. In the same way with variant, we can pass in a greater sum. We only have to specify the sum, the parts of the sum that we care about, and we can pass in different shapes other than that. But it would still just have to specify default in case it didn't match. And this is just some, because it's not embedded into the language, it uses a combinator library for, or a combinator syntax for doing kind of pattern matching. So it uses this case function and on. And so you define your cases for your tags, and the tags use this sproxy syntax. That's just like a type level string, and that's how we kind of map a string to like an actual tag at runtime. Compiler can fill that in for us. And this is just illustrating like the default. So I might take a variant that is polymorphic in V over here at the end. So I only care about the foo and the bar tags, but I can pass in any other tags as well. But that means that I have to then provide a default case in case it's one of those that I haven't specified. So this idea is that we take this variant type and apply it to exceptions, because our problem was that if one's exception type over here, it doesn't combine with another exception type over here. So let's look at kind of translating maybe one of these exception types. So here's this HTTP error. We've got this like, this is just a few, I've only enumerated a couple cases, but it might be bigger. And so this HTTP server error, not found, other, and this uses the familiar data syntax. And so the first thing we're going to do when we want to use variant is we're going to kind of translate this shape into rows where you have the label and the value. So instead of this data type, we're going to define a type alias, HTTP error, and it's going to have tags for each of the variants here. And the right-hand side is then the value that is associated with that tag. And the key that we want is then to open this row. So we've added this R variable. That's the key to polymorphism, like structural polymorphism, is that you have this extra variable R, so that a user can then fill in with another shape, with more, or an extension of the shape. And this is just some syntax. I've made a PR to the type level prelude, but this is just like a type level operator that is, it's just an application syntax, kind of like the dollar operator, but it's just specialized for row types, so that we can combine, we have some syntax for combining these kind of like open type aliases. And this gives us, we then pull out each constructor. Now, so we've got each constructor in their own type alias. And then we then combine them together down at the bottom with the syntax in a larger type. And this is just a helpful kind of way to group, because each variant is on its own, each tag is on its own. It's not really part of a greater type, it's just a tag on its own, but we can have other type aliases to kind of give us the same convenience of the larger type.
What is the plus study? This is a comment.
The plus, so that was just what this row apply is, this infix R 0 type, row apply as plus. So this is application, like type level function application. So it takes an open row like HTTPR on the left-hand side. It's got this R type variable, and it's got rows on the right-hand side, and it just uses, it's like exactly like function application. But what it does is it just lets us remove parentheses. Same idea as value level application operator. Because otherwise you just have nested parentheses. And then, since it's not embedded in the language, it has a little bit of boilerplate, so we do have to define our constructors. And these can be done anonymously, but it's often useful to have aliases here. And so we just define, and this inject, this INJ inject is just a way to lift the value into the variant type. And you provide the tag with it, and it associates that tag. It puts that into the structural sum. Does that kind of make sense? It's just a constructor for variant. So it just takes a tag. That's what this S proxy HTTP server is. That's just the tag that we want to, in particular, lift into the variant type, and it just uses that to map it to the row, to map it to the HTTP server row here. So that's how it uses that S proxy in the inject to associate a value with the row in the type. And so now we're gonna define a type alias here, because if you want all these to work together, they all have to use the variant type. That's the one consideration. So we're going to define a type alias here, except V, which is just except T over the variant type, and the exception types are always going to be rows. So we're going to modify our get signature. It's going to use this HTTP error alias that we just defined, which is that set of rows, and it's going to have the +R off to the side because it's using an open row. In order for them to work together, they have to use an open row. The same thing with write. And this defines, it's only using FS error. And then when we go to use them, they automatically work together. We've just now extended the set of exceptions in the type signature to include both HTTP error and FS error, but we didn't have to modify any code. We didn't have to map over the exception type to then make them unified, because they're already unified by being inside variant and using a set of rows that unify together via the open row. And so one good thing about rows is that their inference is complete, which means that you don't need type signatures and that the compiler can always infer them for you. So if I use the same variant type, but I leave off the type, I've inserted an underscore here, which gives us the type holes, or the wildcard, and it'll tell us back, these are all the exceptions that are used in your block of code. So it enumerates all of the HTTP exceptions and all of the file system exceptions. I didn't go through the file system exceptions, but just assume that those are the file system exceptions that are included within FSA. So I've actually bundled this up into it's a super small library, but so then we come to how do we handle these exceptions? So this is just some syntax here. I'm going to take this get PureScript code block that I've already defined, and I'm going to have this handle error function. And in order to handle an error, we provide a record of handlers where the labels in the record are functions for that tag. So it's kind of like a case statement where you're pattern matching on the constructors, but here we're using the labels in a record to map to the labels in the variant type to eliminate. So each field in the record is a function that handles that particular value for that variant. And this will eliminate the rows from the type. Once you handle a row, it's eliminated from the type. So this is what the inference for this particular block would infer, that both HTTP server error and HTTP not found are no longer in the set of exceptions that are raised because I've handled them. So this is going to look at kind of what the type of this function is. Kind of on, at a high level, what it does is it takes a record of some handler types. We haven't defined what that is, but it's going to be it's a record, and it's going to have some rows of handlers. And then in except v, it's going to take our rows in of exceptions, and it's going to produce a new set of rows of exception rows out of it. And so we have to then build this association between all those three type variables. That's what I'm about to get to. Is like, yeah, so this is at a high level what it is, and we have to figure out how do we define the association between handlers, exception in and exception out, so that it actually type checks. And this is what kind of what variant provides to as well. So row 2 list is something that is in type level prelude. It's kind of a compiler solved thing that turns a set of rows into a type level list, like an association list, so that you can actually kind of use type classes then to operate on that list of rows. So the first thing we have to do is turn our rows of handlers into a list, but we can then kind of recurse on those at the type level. And so variant match cases is a type class that's part of variant. What it does is it takes our input rows, RL, and then based upon that, it infers the types in our variant that are handled by that set of rows. So it looks at all the tags in that record, and it says, okay, these are the variants that were handled by these rows of records, and these are the types that are expected based upon the function argument. So it looks at like it looks at the argument to each handler, and it determines that, okay, we've got this label, and the function expects this argument at that row. And then it asserts that they all unify in the output type except v2. So it pulls out that except out from there. And this is something that's actually really important, the way the unification works. So the except out, it asserts that those unify, but then we also have to then take the union after that. So union is another compiler solved instance. It's a three-way union that kind of can propagate based upon like the direction that you're trying to solve. So it has a left and a right-hand side and an output side. And if you provide the left-hand side and the output side, then it can infer the right-hand side. And likewise, if you provide the left hand and the right hand, it infers the output. And so you can kind of work backwards and forwards depending on what your needs are. And so we use the exception handle and the exception in to then compute the exception out, which is not actually the union. I mean, it's a union of exception handle and exception out, but we only have exception handle and exception in as our input. So it then infers what our output exception types are based upon what we handle and what our input is. And this is just the implementation of it. It's pretty simple. But all this basically does is it pulls out the either from except t, and then on match is a combinator from the variant library. And so it tries to handle our cases, and then our default is to just rethrow the error. And since we can actually prove that we've handled all exceptions now, it's helpful to have a combinator that can then completely eliminate the exception wrapper. So this is like exhaustive handlers. We've handled all of the exceptions in our type, and our inferred exception type is just TO. It's just we've handled everything. It's just an open row at that point. Well, it's just that's whatever the user wants it to be, which means that it can be the closed row of nothing.
Oh, okay. Yeah.
So in that case, we provide there's a combinator safe. So if we have an except wrapper that can unify with the closed row, we can completely remove the except wrapper and just pull out the MA out of it. We don't have to deal with like a left or right. Like normally when you have except T, if you want to get the value out of it, you have to handle whether you have a left-hand side or a right-hand side. But since we proved that we've handled all the left-hand sides, all the errors, then we can just pull out the value. We don't have to deal with like the extra either wrapper around it. And this actually, I mean, it's unsafe technically because I mean there's no association between a closed row and like the left and right constructors. So it is unsafe, but I mean the implementation is technically unsafe, but it is safe in practice.
Really nice to see safe equals unsafe.
Safe, yeah. Exactly. That's about 90% of writing PureScript library code. Yeah. Yeah.
You've done the work for us.
Well, I mean, there is some unsafe somewhere happening because somebody has to provide it somewhere. So whether it's there or whether the variant library, I made a ticket on the variant library to provide a coercion between a closed row and the void type, and that would be one way of handling it, to do it safely. And that I could like pattern match and know that the left-hand side isn't handled, so I can just provide the absurd. But this lets us, because now we've applied the safe handler, we just get the M unit out of it. We don't have to accept V anymore. And so that's all it is. I mean, there's a PureScript checked exceptions library, which just has these two combinators in it. That's all it is. And just to kind of show you that it's not all BS, these are these functions in the library. So this is our, just to mess with it, get PureScript here. This is the, I provided no handlers, and the inferred type is our normal exception types. So then if I provide fs file not found, I'm just going to ignore the argument because this is just for general purposes. Save it. You no longer have the fs file not found. And you can also rethrow exceptions, and that works fine as well. So if instead of fs, we're going to handle fs file not found, but we're going to throw, I define other, find this type other error, or this value other error. Now when I infer it, I've handled fs file not found, but I have this new exception other error. Okay. And then you can also, so say I handle fs file not found here, but I have another handler. So fs, we'll do fs permission denied. But I'm going to throw error, I'm going to throw fs file not found. So I've handled one file not found, but in one of my handlers, I'm going to rethrow another exception. And I'm probably missing, oh, I'm missing that. Now if I look at the type, fs file not found is back in there. So I've handled it in one case, but I've rethrown it in another handler. So I then have to take, I have to count for the possibility now that fs file not found is thrown again. Yeah, Bill. Yeah, so that's, you have to have duplicate labels. That's kind of like the use case for duplicate labels is exception handling. Like if you remove a label, or if you remove a label from a row, but when you're removing it, you want to add it back again, you have to deal with duplicate rows. So if you don't allow duplicate rows in your row system, then you can't do this sort of behavior. That's kind of, yeah, but it doesn't, no, it doesn't. If you try, so if you already have, so let's do this. So I'm throwing this file not found. And file not found is a path, which is just an alias for string. But say I want to define a new one. And I'm going to leave off, I'm just going to leave off the type. You can rely on inference for that file. And we're going to inject just a unit type. So instead of a string,
Need that too.
do I, oh, do what? What am I doing
Your
now?
file not found versus file not found too.
Yeah, but no, I want the type of this followed by it. Oh, you're right, yes. So now I'm using file not found unit, but file not found here, the other one is a path or string. So say I'm throwing this file not found with the string, but if I throw it again, fs file not found 2, which is a unit, I'll get a type error because it'll say string doesn't match with unit. So within the same context, you can't have two different labels mapping to each other. Like actually at runtime, there can't be more than one inhabitant at a given label. So based upon the handlers, it can infer kind of the way that you handle errors, like you push and then you kind of push and then pop like the different errors on the like the set of rows. But at runtime, it can only have one inhabitant for a given label.
How do you handle the second?
That's part of. You mean when you like rethrow it?
Right, so like you have the handler up at the top,
Yeah.
and then you throw it again, so now it's not handled.
And so that's where the duplicate rows come in. So when it actually goes to infer the set of rows for this block of code, it sees two labels, like the type system sees two labels. It'll see file not found, and then another file not found. But I'm handling this first file not found, which then puts this other one at the top of the stack. And so it kind of like pushes it down on the stack at the type level on the set of rows. And as you handle it, it pushes them off, and so then you get it back again at the top, at the beginning.
So could you run this through another handle error?
Yeah.
That handles that one.
Yes. So if you then do, so let's do. So I'm throwing it here. I'm going to. I'm going to do another handle error. I'll catch it here, fs file not found. And then we'll see file not found isn't there anymore because I've handled it twice. And I can even wrap this. I'm going to do this. I'm going to move this. And we'll see that it's also removed. There's also no fs file. So that's kind of like the magic of rows, and like this framework is also working with polymorphic variants. It's like polymorphic variants are really neat in as a solution to the expression problem versus like using type classes or something. They're kind of like more of a direct style of like dealing with that problem, because you can then zero in only on the part of the structure that you care about. So that's all I got. Any other questions?
This is delightful. I'm really excited about it. One kind of weird question. We have little polymorphism for polymorphic products. This is for sums. So why didn't you call it column polymorphism?
Column. Well, there's already existing. So like OCaml has polymorphic variants, and that's just what they're called in kind of like the literature that already exists out there. That's so. So yeah, in OCaml they're known as polymorphic variants, and so this is just the same idea but in PureScript. Yeah.
Cool, thank you.
Yeah. All right.